Welcome to Ready to Derive. All our work on derivatives to date finally gets us to a place where we can start exploring applications of calculus to the real world. Derivatives allow us to give precise answers to questions that we could have only answered by approximating. In this lesson, we will learn about projectile motion, a fancy term for tossing objects in the air. We will only look at the case where we project the object vertically, like this. So here's a person with a ball in their hand, and they toss it upwards, upwards, upwards to maximum height, and then the ball returns back to the ground. We will not look at cases where we toss the ball at an angle or the object at an angle, as that would make the mathematics more complicated, and you can get that in physics anyway. So without further ado, let's get started. Let's begin with a scenario. I hope somewhat realistic. I have never used a potato launcher, but they do exist. They look like a lot of fun. So here's one that's used to launch a potato vertically into the air with an initial velocity of 50 feet per second from a height of 6 feet. Now, the formula for height in terms of time would be given by this. And this actually, this formula can be derived using calculus, but we're going to just give it to you as is. I hope you realize that there's some important positions here. So, for example, the initial velocity 50 happens to be next to a t. The initial height of 6 sort of stands alone. And this negative 16, we'll get into that a little further into the video. So let's just sort of practice using this formula and see what we get. So let's take some time from seconds, 0, 1, 2, 3, 4. And we get to just use the formula by plugging in. So if we would like to know what h of 0 is, we just plug 0 in there. We would get 6. Ditto for t equals 1 second. Plug that in, and we would get that the height is 40 feet, etc. If you were to continue this for 2 seconds, the height of the potato is 42 feet, 12 feet, and then negative 50 feet, which means that 4 seconds it's well below ground. So obviously it hits the ground somewhere between 3 and 4. And here is a sketch of it, and we can see here is 0, 6. Let me use another color, 0, 6. And then at 1 second, it's up here at 40. 2 seconds, it's a little higher here at 42. 3, it's at 12. And then 4, it's below ground, technically, or we don't even count that. So you can see that there's some really interesting features. We might be interested in sort of when does it reach its maximum height? What is its maximum height? And many more questions we can answer using calculus. So here is the height function, again, of the potato, and here's a graph of its height versus time. So I neglected to actually label my axes. So height in feet is on the y-axis, and time in seconds would be on the x-axis. Now bear in mind that this is not the path that the potato follows. This graph does not show the path of the potato. The potato is being launched vertically. It travels vertically up and then back down. So if we were to launch it at an angle, the formula would be more complicated. The analysis would be more complicated. So we're keeping it simple. So we can answer a question like, when does the potato reach a height of 40 feet? And we already know we got lucky in the previous slide, we had put in t equals 1 and we got out 40. But there's obviously another time at which this happens. And we need not much more than pre-calculus to be able to answer a question like this. We would just set the height equal to 40, and we would solve a quadratic. And if we brought 40 to the other side, we would have this quadratic, 50t minus 34, and that can be factored. I mean, you could use a quadratic formula, or if you would like to challenge yourself, you could pause this and try and factor it, and it would come out to this, which gives us 2 answers. T equals 1 second, which we already knew from the slide before, and t equals 17 over 8 seconds, which works out to be 2.125. So so far just using pre-calculus and what we know from before to answer these questions, we could find out when does the potato hit the ground. We knew from the previous slide that it hit somewhere between 3 and 4 seconds, but why not solve it properly? So make the height 0, find out at what time the height will be 0. Now, this is not factorable, so you could use the quadratic formula. You would get out 2 answers, one of which would be negative, which we would ignore because it's not applicable, and the other answer comes out to be approximately 3.24 seconds, approximately. That's when it hits the ground over here. And there's even one more question we could answer using pre-calculus. When does the potato reach its maximum height, which looks around, let's see, get that blue, it looks around up here. And in pre-calculus, we would use the formula for the location of the vertex, which is negative b over 2a. And that would be negative 50 over 2 times negative 16. That would come out to 1.5625 seconds. But we kind of just had to trust that that worked, and it did work. But why does that work? Well, it's calculus really that informs that calculation, as we will see on the next slide. So let's get some calculus going here with the first derivative to the rescue. Now, what would the first derivative of the height function be with respect to time? So think about it, the instantaneous rate of change of height of the ball with respect to time. Well, that's none other than velocity. So let's take the first derivative here. So the first, we're going to call it h prime or v. So h prime t is the velocity function. And if we take the derivative, let's see, by the power rule, we would bring that 2 down to make that negative 32t. For 50t, that's a linear function. So the slope of that, or the derivative of that, would be 50. And the 6, the constant, would disappear. So let's have a look at that same problem from before, but we're using calculus. So when does the potato reach its maximum height? Let's think now in terms of what we learned so far, tangent lines, etc. Well, maximum height we know is at the vertex, but what is true at the vertex? The tangent line at the vertex has a slope of 0, which means that h prime here, or aka the velocity, would equal 0. So all we have to do here is take our velocity function to find when it reaches the maximum height, set it equal to 0. This would give us negative 32t equals negative 50, and t equals negative 50 over negative 32. That should ring a bell. We just did that calculation on the previous page, and that comes out to 1.5625 seconds. So that is where the negative b over 2a formula comes from. It's calculus. We can even answer now, what is the maximum height it reaches? This is not calculus. We would obviously just take our original function, h, our height function, and plug in 1.5625. And if you did that, you would come out with 45.0625 feet. So thanks to calculus, now we understand that the potato will reach its maximum height at 1.5625 seconds, and that the height, its maximum height, is 45.0625 feet. So thanks to calculus delivering us the velocity function, we can answer some interesting questions about the motion of this potato that we would have not been able to otherwise. So for example, what is the velocity of the potato when t equals 0? Well, that of course would be the slope of the tangent line right here at the moment the potato is released. And we get to just plug in 0 into our velocity function. And we come out with 50, and don't forget the units, feet per second. And this shouldn't come as a big surprise. This should be familiar because this was the initial velocity with which the potato was launched in the first place. And then now we could ask, what is the velocity of the potato when t equals 1? So that would be the slope of the tangent line there at t equals 1. Again, We would plug 1 in. We get negative 32 times 1 plus 50, which would be 18 feet per second. So notice that both velocities are positive. That's because the potato, is being projected upwards, and upwards is considered positive direction. Notice that at 1 second, the velocity is significantly less, and that's because gravity is acting on it. We know at the vertex of the parabola, the velocity will be 0. So we can anticipate that on the way back down, the velocity will be negative. So let's look at one more. What is the velocity of the potato when it hits the ground? That would be the slope, excuse me, let me use that, the slope right here of the tangent line. And so we would plug in 3.24. We found out the answer 3.24 on the previous slide, and that comes out to a negative 53.68 feet per second. And that's the impact at which the potato hits the ground. It's faster than the initial velocity in absolute value sense, because of course the ground is lower than where it was launched from at a height of 6 feet. So if the first derivative delivers us velocity, what would the second derivative of the height function give us? So here's the height function, the velocity function is the first derivative, it's the rate of change of height with time. So the rate of change of velocity with time, well, that's none other than acceleration. So let's take the second derivative, and we would, if we took the second derivative, we would be left with negative 32. The t would disappear, as would the 50. And that should come as no surprise. Negative 32, what are the units of that? It's feet per second squared. And that's the acceleration due to gravity on Earth. So notice that is independent of time, right? That's a constant, no matter where you are on the Earth's surface. So what I like to do here is just sort of show you the relationship between velocity and acceleration. Sometimes students have a hard time understanding exactly what those units mean. So let's just look at a few samples of the velocity. We already calculated some of these in the previous slide, but just to show you the pattern that's going on. So we would plug in 0 here, and we would get 50 feet per second, as we discovered before. Here we would plug in 1, and we have 18 at t equals 2. We would get negative 14, and at t equals 3, we would get negative 46. Now, what's really neat about this is let's look at the change in velocity over time. So if we, over 1 second, the velocity goes from 50 to 18, and that's negative 32. That's a reduction of negative 32 feet per second. And the same is true here, negative 32 feet per second. So, and once again here, because obviously the slope of the velocity function is indeed negative 32. And so what that means is, so this is acceleration here. What that means is negative 32 feet per second squared literally means that the velocity decreases by 32 feet per second every second. So let's just summarize what we've learned about projectile motion. So for our potato, let's recognize what these various coefficients represent. This was, the 6 was the initial height. The 50 was the initial velocity. And notice that the negative 16 is really just half of the acceleration due to gravity, so it's just half of g. So we can generalize this formula by replacing, by acknowledging that the coefficient of the t-squared term would be half g. That's the acceleration, g being the acceleration due to gravity, so this could be used on the surface of any planet. This would still apply. V0 stands for the initial velocity, and h0 stands for the initial height. And if this is the height function, then taking the derivative would give us the velocity function, which leaves us with gt plus v0. And notice there that v0 is the initial velocity, and then you are just going to be basically subtracting multiples of the acceleration due to gravity here for every second that elapses. And then taking the second derivative, we get the acceleration function, which delivers us g, the acceleration due to gravity, which is what we would expect. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.